Okay, I want to look at problem 5.28. It's page 92 in the workbook. If that helps. All right, I don't always remember to write the page numbers up there. So you might open that up and take a look at it. And the idea is we're going to have a pulley system with some scales, and maybe I should just show you what it looks like in the real world very briefly. I hinted at it in the last video. Come on, come on. All right, there we go. So you can kind of see this, and I apologize, nothing's ever going to be perfect here. But what's happening, and maybe I'll move this one out of the way just a little bit. See a little bit better there. We've got these two masses. All right, and you can see this one right here is about 1.02 kilograms. Notice that's 10 newtons mg. All right, and then this one over here, it's resting on the ground right now, but if I lift it up and hold it, you can see this one's got a weight of about 12 newtons because this is 1.23 kilograms. So notice it's about 12 newtons. Apologies if you can't read the scales from there. Obviously, when I let it go or move it, that scale reading can change. I'm going to set this on the ground so I don't forget. Gee, the ground's exerting a normal force of about 2 newtons. Okay, whatever. Now, in this case, remember, what do scales read? They read the tension in the string. So in this problem right now, I want us to ignore the mass of the scales, and we can address that at the very end of the video or in the next problem. I think 5.29 tells you how to do that. But so for now, let's assume the scales are pretty light. They are. I think the scales are 10 times less mass than these sandbags here. So you don't really have to worry about the mass of the scales too much right now. All right, and let's go back to our pictures here. Let's go back to here. I think I want to go here. Whoops, wrong way. Come on. Gosh, sorry. There we go. So in this case, again, the masses are right here. Those correspond to these weights. So it's about 10 and 12. We saw this matches to the experiment I have set up. Great. And at the very end, we can do all the numbers in the real world if you want, or you can stop the video if you learn what you need. Now, it's important that we understand some common assumptions. I don't want to belabor this a lot, but I want to talk about it at least briefly one time. When we're using pulleys, a lot of times what's going to happen is one object's going to go up and one object's going to go down. Well, in this case, we can simplify the problem dramatically if we could just call this letter A. Under what circumstance will the magnitudes be the same? Obviously, the acceleration vectors have different directions, but the magnitudes could be the same. The idea is if we see an inextensible string, now, what does that really mean? Not stretchy. So the idea is if we use a string that's not stretchy, right? When this one moves 1 centimeter, that one has to move 1 centimeter. Or if this one moves 2 feet, this one will move 2 feet. That means they're going to move the same amount. Well, derivatives of those, or velocity and acceleration, will also be the same. If you don't know derivatives, that's okay. So basically, if you have an inextensible string, that's it. Not stretchy string. If you use bungee cord, right, one of them might stretch more than the other. The heavier one might move a little bit faster because it stretches the cord a little bit differently or something. Great. Now, I'm going to make the assumption that acceleration is constant. Strictly speaking, that's not true, but it's pretty darn close to true. The idea here is if the string is light, or sometimes we'll say massless, or relatively massless, or sometimes they'll say relatively light. So if you have a light string or a massless string, obviously no string is massless, but we mean massless compared to this. Well, think about this. String is maybe a few grams versus these sandbags, which are several kilograms. So this is way off in the 4th decimal place. It's totally reasonable to ignore the mass of the string. Why is that true? Think. if you had a heavy chain connecting these, well, as block 1 went up and block 2 went down, more of the chain links would be on this side. If you had more of the chain links on this side, the mass would be increasing on this side, and then the acceleration would get ever faster. So it's not that that doesn't happen in the real world, like with a heavy anchor on a boat or something. But in our experiment, if the string is massless compared to the other masses involved, then we can say acceleration is pretty much constant. All right. So that's why. Lastly, the tension magnitudes are equal if the pulleys are massless. So if you have a massless pulley, or sometimes they'll say massless, again, massless relative to the other masses involved. All right. We will learn what to do in the real world in chapter 10, which is usually physics 161 or a later course. Chapter 10 will discuss massive pulleys, pulleys with mass. So it's not that for now, our assumptions are going to be these things are true. And what does that do for us? If we say these things are true, the tensions don't need subscript. The tension in the string is the same throughout. The acceleration doesn't need subscripts, and the accelerations are the same throughout. We still need subscripts on the mass. And just to show you this isn't lies, let's go over and look at the experiment, and I'll show you, because I've got these scales in there, that this is approximately true. When we run this thing, let's go over there. All right, and let's autofocus. Now, I apologize if you can't see these scales exactly. I'm going to do the best I can. And now, when I'm touching it, that's a different problem. So what I'm going to do is I'm going to pull this thing down. As soon as I let go of it, watch the scales. They should reach the same tension. Now, I'm going to have to stop it before it hits the top, or it might fall down and break, and I don't want that to happen. So when I let go of it, I'm going to do this one more time. When I let go of it, watch the scales. They should be the same. Okay, I don't want it to break. I hope you had enough time to view that. But so hopefully that was at least approximately true there. Oh, there we go. We push it down. Oh, wow. It's spinning. All right. This is getting crazy. I do not want to break this and have to redo it. All right, let's set that up. Let that unrest. Okay. And hopefully you saw the blocks moving about the same amount. All right. Come on. Why don't I just put batteries in this thing? Now let's do this. Oops, wrong way. All right. And so what we want to do now is I want to analyze this problem that used those assumptions. I want you to draw a free body diagram for each of these two masses. And I'm going to do that, and then I'll move the camera over. So you can take a second, or you can see if you can race me. I'm going to draw the free body diagrams right here, and then we'll get rid of this picture. So race you, go. I will move the camera over in a minute. This is FBD 1, and I will put the, okay, there's some tension. It's going to be this term. And then I'm going to draw this going this way. And I've got my coordinate system. Oh, I should explain that coordinate system to you, shouldn't I? I'll do that in just a second. Okay, I've drawn my FBD for the first one. Let's just do that. Come on. So there's the FBD for the first one. Tension is up. Did you remember to write M1G? Because they're not the same mass. Acceleration's upward. Why did I do this weird thing with the rotated coordinate system? Imagine we're following that string around. The other coordinate system is going to be upside down. This is a cool trick. You line up one of your coordinates with the acceleration vector in the string, and just follow the string around. And that'll give you the other coordinates. So if I go back to this one, is it this button? Right, the idea is I start with this coordinate system and I wrap it around. And notice I get this, that's why I flip this one upside down like that. It feels weird, probably. Just trust me, I know what I'm doing. Do what I do, just trust me, okay? So now draw the other FBD really quick. Then I'll move it over for you. Get the coordinate system right. Okay, I'm gonna bring the camera over. Here's what I've got. Doing board 1. There's the other FBD. Again, the coordinate system flips because I'm letting my acceleration be the way the masses were accelerating. They were going towards the heavier one. M2 was the heavier one in this case. All right, let's keep rocking here. Force equations. Pause the video or see if you can beat me. Write the force equations. Okay. In this case, I get tension minus M1G equals M1A. Get those subscripts on there. I don't need subscripts on these because of this garbage. Great. Okay, and I don't have an X equation, so I'm just going to leave it at that. Watch out. Pause the video. Do it yourself, then see if you screwed up. Go. Trying to block it so you can't be watching me. Get out of the way in a minute. Is that what you got? Look, the coordinate flipped. These two have the same sign. I don't care what coordinate system you use, but in this case, people usually remember F equals MA, not F equals plus or minus MA. So by lining up your coordinate system, you won't screw up the MA, but then you have to think, these two are the pluses, this one's the minus. What is the internal force? Tension. I know it seems weird, but right, you could imagine this as a system, and you could actually visualize this as a 1-2 system with, what is this direction? I guess that would be what, clockwise, I think? Clockwise is the positive direction. Maybe you see why I'm setting you up this way. This starts to get into circular motion. Later on, when we have problems in circular motion, we could either call clockwise or counterclockwise positive. And essentially your coordinate system rotates around, just like the mass on the string. So it probably feels annoying to do it this way. Could you do it the other way and get full credit on a test? Yes, but you should learn this way because it makes more sense and you get used to it in the long run. All right, well, there's two obvious things we can figure out. One is we can figure out the acceleration. The other is we can figure out the tension. If you want, you've got the answers in the workbook. If you don't want to watch the rest of this video, just follow along with the workbook. What I'm going to do is I'm actually going to do this problem, solve for T, solve for A, and then I'm going to get out a stopwatch and predict how long it should take for the mass to fall down and see if we're right. So if you don't want to do all that, just get the workbook problem done and check the answer. That said, go for it. Solve for T and solve for A. I'll let you figure out which one's easier to solve for first. Okay, I'm going to do it. I'll let you watch while I do it live. If you want to pause the video, you can. If you want to watch me do it live, you can. Let's go over to board 2, though. All right, I'm going to run out of room, so I'm just going to rewrite those force equations over here. I got T minus M1G was equal to M1A. And I also know that M2G minus T equals M2A. We're trying to find both T and A, the tension, magnitude, and the strain, which we can check against the scale and the acceleration. All right, in this case, I'm going to add these equations. Because I use a rotated coordinate system, look at how cool this works out. The tension drops. It's internal. The internal force drops out if you use this rotating coordinate. So I get M2G minus M1G. On this side, I get an M1A plus an M2A. I hope you believe me that that's M1 plus M2 quantity times A. Right? You add them and then you factor out the A or whatever. Now look, on this side, I guess if I was smart, I should have factored out the G. But I'm going to rearrange this and say A is equal to something. You go ahead and do the algebra, pause the video if you want. Here I get G times the quantity M2 minus M1 over M2 plus M1. The order doesn't matter in the basement, so I just flip the order there. So that's the acceleration magnitude, all right? Well, in this case, I think we even have the masses here, right? So I'm going to plug in what these were. G was 9.8 meters per second squared. I'll explain why it's better to do it algebraic first. What was M2 and M1? M2 was 1.02. I'm just going to write that somewhere. M2 was 1.23 kilograms. M1 was 1.02. All right, so you know what? I'm just going to punch this all in here and just get a number to save board space. I'm going to need it, okay? All right, so 1.23 minus 1.02 divided by the quantity 1.23 plus 1.02. So that's 0, and then times that by 9.8. I got 0.915. Okay, so there's a number for that. Remember, you want to do this algebraically. Check this out. You could check the units. I could use grams over grams and the grams would cancel out, or I could use kilograms over kilograms. That's kind of interesting. We see that by doing it algebraically. Here's another case. We can think about special conditions. What's one special condition? What if the two masses are equal? If the two masses were equal, the acceleration should be 0. That makes sense. If you have the same mass on each side, it should be balanced. That doesn't mean it's not moving. It means if it's moving, that motion rate is not changing. Okay, this is acceleration, right? Acceleration is change in velocity. So you can have the same mass and still have motion if you push it and give it a start. What else? What if mass 1 was 0? What if I took the string and cut mass 1 off of there? Well, if mass 1 was 0, the other mass should just fall straight down in free fall. What if I cut mass 2 out of there? Look at this. The acceleration would be negative g because it would go the other direction at rate g. So by writing these things algebraically, you can kind of think through various conditions and get a feeling for if your result is correct. You're going to ask many different what if questions, which is another way to check your work, not just check the units. That said, let's go ahead and figure out the tension. And so that we don't get ahead of ourselves, let's get an algebraic result for the tension by plugging in the algebraic result for A and then simplifying it. Okay, you got the workbook if you don't want to watch this, but then we'll confirm this number with measurements in just a minute. Okay, so I'm going to solve, this one looks as easy as any to solve for T. So I'm going to pull this over here. T is equal to M1G plus M1A. Now there's a little bit of algebra we can do here. Ugh, it looks ugly. Well, let's just deal with it. You got to learn how to deal with this stuff. So if you're not willing to be patient and sit through it, this is not the right class for you. This is not the right major. You have to be somebody that's willing to plug this in and simplify it and enjoy that bit of pain. Okay, that's just the facts of life. You do a lot of algebra here. If you're a CS major thinking, oh, why would I ever want to do this, right? A lot of times when you're making a code, you want to do the algebra as simple as possible. That way your code can be as fast as possible, right? Reduce the number of computation steps. So I'm going to keep going here. I see everything's got an M1G there. I'm going to factor that out. M1G, there's a 1, this M1G pops out. Well, I'm going to use a common denominator here to clean this up. And you might be saying, this seems silly. You're just doing silly stuff. Well, just trust me a little bit. I have some experience with these things. A lot of times doing the common denominator will clean things up. And I think you'll see why in about 10 seconds. There's the common denominator, right? I just changed this to M2 plus M1. Isn't this just M2 plus M1 over M2 plus M1? I don't know if you can see that. Zoom, come on now. My screen's falling asleep. All right. When I do that, then I get a special result here. This drops out and I get a 2M2. That's a lot easier, actually. So we first made it more complicated, but then we get this weird result over, what is it? Let me make sure I didn't screw this up. I get M2 plus M2, that's 2M2. Then I can multiply that, so I get a 2, and then that's the whole numerator. So I get a 2 M1 M2G. Interesting result. There's some weird ways you can check this. Number one, if you switch the masses and you put 1 on one side and 2 on the other side, you should get the same tension. Well, that means if you switch the subscripts, the result should still be the same, and it is. That's a weird check, isn't it? Again, this should be symmetric if you change the sides. That means it should be symmetric if you change the subscripts, which means your answer should not change if the subscripts all flip. That's checks. The units check. Tension is in newtons. This is a kilogram times a kilogram. Let's just do it. Kilogram times meter per second squared all over kilogram. Right? Kilograms plus kilograms equals kilograms, not kilograms squared. Well, we could see that we better not use grams for this result. That's cool. And then probably some other things, right? If the masses go up, we see the tension goes up. So this seems reasonable. What if the two masses are the same? If the two masses are the same, what do you get for the tension in the string? So let's say we basically, imagine if both of these were 1 kilogram, which means the tension or the weight of one of them would be 10 newtons. Is the tension going to be 10 newtons, 20 newtons, 5 newtons? What? Look. If each of these is 1 kilogram, I get 1 over 1 over 1 plus 1, which is 2. The 2 drops out. The tension in the string should be the weight of one mass if they're equal, not both of them, right? Interesting. All right, you can ask me more about that in office hours if you care. Anyways, this is looking pretty good. I'm going to punch in the numbers here and just get a number for it. Usually, the tension should be somewhere between the two weights. Hopefully we find that result. So 2 times 1.02 times 1.23 times 9.8 divide by parentheses of 1.23 plus 1.02. I got 10.93. So when we run this, notice that's about 11 newtons. The two weights, this is why I picked them. One of them is about 10 newtons, one of them is about 12. And notice 11 newtons is the tension in between. 11's bigger than 10, it pulls it up. 11's less than 12, it's not enough to hold it up. That one falls down. We're going to run this thing, and then while I'll do this one, I might grab a stopwatch too. I'll explain why. In order to get this acceleration, I'm going to need a stopwatch. Again, you don't have to watch all this video if you don't want. I'm going to do it because it's kind of exciting to me. All right. First, let's go. Let's get over there. 8. Again, showing you these scales. I'm holding it, the scale reading on that one should be about 12. On this one, the scale reading should be about 10. I'm making up for the difference by holding the string, and I forgot I gotta grab a stopwatch real quick. Hold on. Grab that out of the back. Exciting video. Neat. And I need a meter stick. Oh crap. Forgot my meter stick. Let's just get these two 1 meter. Okay. So this is 1 meter off the ground right here. So this is 1 meter off the ground. This is about 1.92 meters off the ground. So we expect 1.92 meters of travel. I'm going to write that down so I don't forget it. All right. Now, I'm going to run this thing, and I'm going to let go of it, and hopefully you can watch two things when I run it. Okay. Watch the scale. We expect the scale to read 11 newtons. And then when I run this, I'll time it, and we can verify the acceleration with kinematics. Here we go. 1 banana, 2 banana, 3 banana, 4. All right. Oh my God. I got about 2 seconds. I hope I timed that right. All right. Let's see. Whew. I was worried that would happen if I. All right. So I didn't do a very good job timing this thing at all because I was worried about getting hit in the head. What was I doing? Board 2. All right. Here we go. So hopefully you saw the tension was about 11 newtons. If there's a discrepancy, why? We ignored the 100 grams of each scale. That's going to change things a little bit. Okay, and then here, let's get this acceleration. I know delta y equals 1/2 a sub y t squared. So that means the time we expect, let's see, well, we got, how about this? Ay is equal to 2 delta y over t squared. I found my time was about, what did I say, 2 seconds? Oh gosh, I was falling. Yeah, so let's see. If we have 2 times 1.92 divided by, I had 2.08 seconds, 2.08 x squared. I got 0.89 in my experiment. Again, we see that my acceleration is a little bit lower. Why? This makes sense because we had 100 grams on each scale, or maybe it's 150 grams for each scale. Let me see what it is now that it fell down. This is 152 grams. So that's going to increase the mass ever so slightly. And right, that's going to subtract off in the numerator, but not in the denominator, which tends to lower this acceleration. This seems pretty good. That's it. Oh my God, that was a crazy problem. All right. Wait, oh, I think I gouged the ceiling. Oh my gosh, there's a giant gouge in the ceiling from where that scale flew up and hit it or something.